Good day, everyone. I would like to start by thanking the organizers for having invited me. I think that this workshop has a very interesting and complete program. I hope that everybody has the chance to enjoy the talks and exchange ideas. I would like that this talk serves as an introduction to topic that has become very popular in the last few years. I will be covering two problems that we recently worked on. What they have in common is that we apply radio maps to determine the positions that communication UAVs must occupy in space. So, what are communication UAVs? Communication UAV is nothing but UAV with a communication module. This allows them to serve a large range of users, from terrestrial users to aerial users, such as other drones, mobile users, static users, and they find a wide range of applications. For example, they can be used to serve users in remote areas where that are out of the coverage region of the terrestrial infrastructure, by establishing communication links, probably in multiple hubs. They can also offload the terrestrial base station in situations where a large number of users are in a small area. They can be used to establish connectivity with users in remote in emergency scenarios, in remote locations, and very promptly, right? And they also have many other applications, such as smart agriculture. So the fact that we can choose the 3D positions of UAVs leads to the question of where to place them for communication purposes. And to answer this question, we need to consider separately both kinds of communication UAVs. So the first kind is aerial base stations, ABSs. Here, these communication UAVs are intended to serve a large number of users. Generally, they are hovering at a fixed location, right? So they don't move as the users move, and they are called base stations because they implement the functionality of a base station. So a large number of layers, and here the problem is to choose the 3D positions of multiple aerial base stations to give coverage to a certain area or a certain set of users. The other kind of communication UAVs are aerial relays. So these ones are or do not implement the functionality of a base station. They are much simpler from a communication perspective, and they are intended to serve a small number of users. So if the users move, they can also track them, adapt their locations to keep covering those users. The problem in this case is path planning, right? So we need to plan or design the trajectories of these aerial relays to serve the user as fast as possible and possibly track the movement of the user. The idea here is that, or the challenge here is that the quality of the positions of the UAVs as well as the quality of the trajectories depend on the channel from the users to the points in the airspace where the ABSs are. So in principle, to choose a good set of locations or trajectories, we would need to measure the channel from the users to every point in the airspace so that we can choose the best points, right? But that is, of course, not really possible in practice. So the idea in this work is to use radio maps to predict the channel at every location, or between the users and every location in the airspace, without having to send a UAV there to measure the channel beforehand. So, what are radio maps? Radio maps are mathematical objects such as functions or tensors that provide a metric across space. So this metric can be, for instance, the received power. This is an example of a power map which provides the received power, or the power that the sensor would, or a receiver would see at each location in a certain 2D region. So this can be a certain area, or in this case a square on the ground. But they can also provide power spectral density or channel gain, as we will soon see. To construct these kind of maps, we collect measurements at multiple locations, and then we apply some sort of interpolation algorithm. Radio maps have many applications. They allow us, for instance, to detect coverage holes or to control interference. In our case, we'll be using them for their ability to predict the channel at locations where the UAVs have never been. So, how can we predict, or how can radio maps predict the channel gain? So let us decompose the channel gain into its components. So on the one hand, we have this free space loss component. This depends on the locations of the transmitter and the receiver, well, essentially only on their on their distance, right? So we don't really need a map for this, right? Just knowing their locations, it's enough. Then the fast fading, which is caused by multipath, is not really predictable because it changes very quickly, right, at the scale of wavelength, and the wavelength is in the order of centimeters or tens of centimeters, typically in contemporary systems, even millimetric. So it's not possible to predict those variations in practice. We should think of fading as kind of a prediction error or noise. So finally, we also have the shadowing component. This is caused by abstractions. So this component is what we don't know in practice, but we can predict if we have some measurements. So this is precisely what radio maps can do. We can learn the shadowing from measurements. Then if we want to recover the actual gain, we just add the free space loss. So how to learn shadowing maps from measurements? The standard approach is to apply what's called the radiotomographic model, which was proposed in this work here, and that is inspired by tomographic imaging used in medical applications, for example. This model establishes that the shadowing component between two locations, this would be, for instance, the transmitter and this is the receiver, or the other way around. This shadowing is a scale version of the line integral of the so-called spatial loss field. So the spatial loss field is a function that essentially provides the attenuation that an electromagnetic wave suffers when going through the point X, right? So in practice, we cannot really store a function. We need to discretize it, right? So the standard approach is to store the values of L at a set of grid points, right? So that we can call also centroids, these blue dots, right? We can make, in the case of aerial communications, we can make a 3D grid, right? But in the figure, this is a 2D grid. So then, with this discretization, how can we approximate this line integral? There are two approaches in practice, and most work so far have used this weight function approximation. The idea is to create an ellipse where the transmitter and receiver are at their at its foci, right? And then one takes a linear combination of the centroids that fall inside the ellipse, okay? So this has several problems. For example, it may be the case that there are no centroids inside the ellipse, which would predict a zero shadowing, even though this may be highly inaccurate. And the approximation will also be discontinuous. right? So instead, we in our research we proposed a different approach, which is to approximate this SLF as a piecewise constant function, so that is takes the same values in all points of each of these voxels, right? And then we integrate that approximation exactly, okay? So the line integral of piecewise constant function is very easy to compute, and this has a linear complexity in the number of points in each of grid points in each dimension. So after this introduction, we will be applying tomographic maps to each of the problems that we introduced earlier, namely ABS placement and path planning for aerial relays. So let's start with ABS placement. In this context, there have been a large number of works. Some of them consider 2D placement. That means that the height of the UAVs is fixed beforehand, right? So they only need to optimize on their 2D location on a horizontal plane. There are also works that consider 3D placement, so also optimization of the height. However, these works suffer from a very important limitation, and that their predictions of the channel are very inaccurate, and therefore that leads to highly suboptimal placement solutions. So for example, these ones assume that the channel is free space, right? This one assumes that these ones use an empirical model which essentially quantifies the attenuation based on the elevation of the link and whether the environment is rural, urban, suburban, whatever, right? And these ones require 3D models of the environment, right? A 3D model of all the buildings, trees, cars, obstacles, everything, right? Which is not generally available in practice, right? So to address this limitation, we propose 3D ABS placement scheme where the channel is predicted using radiotomographic maps, which therefore we are using the channel at the location where the UAVs will be placed, right? This is much more, or should be much more accurate than any of these approaches. And to do this, we propose a convex optimization criterion that allow us to accommodate no-fly zones, so positions in space where the UAVs cannot go, right? So for instance, they cannot go inside buildings, they cannot go below or above certain altitudes imposed by regulations, they cannot go near airports and so on. And And to optimize this criterion, we propose a linear complexity solver. So to be able to formulate the problem, let me briefly introduce some notation. The channel gain, as I said earlier, is assumed to be composed of a path loss term and a shadowing term. So here this denotes the position of an arbitrary ABS. This is the wavelength, and this is the position of the mth user, which here we can also call ground terminal, as in the literature. And this is the shadowing term, okay, which we will predict using a tomographic map. The capacity is, as we know, a function of the channel gain. So this here is the channel gain in natural units. This is the bandwidth, this is the transmit power, and this is the noise power. Then we'll assume that the lambda, the bandwidth, transmitted power, and the noise power are known, which is reasonable. And we will be assuming that the backhaul is unlimited. That is, the connection between the terrestrial infrastructure and the UAVs has a sufficiently large capacity. So the communication between the UAVs and the ground terminals is limited by the channel in that link and not by the channel in the backhaul, right? This is, of course, a simplification for the sake of the presentation, but the case where the backhaul can be limited is addressed in this in our journal paper as well. So the problem is given the positions of the ground terminals, and given a minimum rate Rmin, the problem is to minimize the number of ABSs such that all users receive at least this target minimum rate, right? So here we are optimizing over the number of ABSs and the positions of the ABSs, right? And this constraint imposes that the sum of the capacity from the mth user to the ABSs is at least Rmin. So a user may be served by multiple ABSs simultaneously. And the ABSs must be inside this set of allowed positions. So this essentially is the airspace, excluding the no-fly zones, such as buildings, as I said. And since the shadowing is unknown, right? The shadowing determines this capacity here. We will be using a radio map to predict it. So, let me briefly describe the proposed approach. And this problem, as we can see, is quite complicated, and these functions are non-concave, and this set may be quite difficult to handle, so it is necessary to discretize the region, discretize the set of possible ABS locations. So we create a grid, which is, for example, a 3D and regular grid, where we remove the grid points that are out of the allowed flight and region, right? So we remove the grid points that are inside buildings, for instance. And if we do so, we can rewrite this problem in this way, where we have defined this variable and this vector for every grid point G. So alpha G is 1 if there is a UAV at grid point G, and it is 0 if there is no UAV at that grid point. Okay, so it's like an indicator variable. And then C is a vector that collects the capacity of the channel between each user and the jth grid point. Okay, so with this notation we can rewrite this problem in this way. Okay, so now we have that the number of UAVs is equal to the sum of these indicators. Okay, and if we change the variables in this way and define this indicator function, then this problem can be rewritten in this way. So now we have replaced this restriction that these alphas have to be either 0 or 1 with this restriction that this variable that we introduced is either the 0 vector or the capacity vector. The problems are equivalent. So since this problem can be shown to be NP-hard, what we can do is to relax it to arrive at a convex optimization problem. So the idea is to use the fact that a vector is 0 if and only if its norm, infinity norm in this case, is 0. And then we can note that the sum of these indicators here equals the 0 norm of the vector that contains the infinity norms of each of these R vectors. These are called R vectors because they can be interpreted as rates. So as we know, the 0 norm can be relaxed into an L1 norm, right? So we can replace this 0 norm with the sum of the absolute values of the entries of this vector. Since they are norms, they are non-negative. The absolute values equals the entries themselves. So this equals the sum of the entries of this vector. But here we also put these weights, because we apply this approach here, reweighting, which allows us to obtain sparser solutions, and therefore the error incurred by this relaxation becomes smaller. This takes us to this relaxed problem here, which is now convex. Okay, so in view of the constraint set, one could think of using interior point methods to solve this. But the problem with that is that that would incur cubic complexity, right, in the number of grid points, and the number of grid points may be very large, right, because we are in a 3D space or region. So what we do is to apply the alternating direction method of multipliers. If one does that in a smart way, we have to try multiple decompositions of this problem until we arrived at one decomposition that results in an algorithm with a linear complexity in the number of grid points. So some simulation experiments. These are in an urban environment, and we will be comparing the mean number of ABSs, right? Of course, we want that this number is as small as possible, as in our problem formulation, and we'll be comparing with 4 algorithms in the literature. So here we have this the metric that I just said versus the number of users. We see that the proposed algorithm gives rise to a significantly lower number of ABSs than the competitors. It is also the increase with the number of users is milder. Here we observe a similar effect, but now we are plotting the mean number of ABSs versus the height of the buildings. As the buildings grow higher, the channels become typically worse, right? Because they obstruct more paths, right? So the problem becomes more challenging to the right, and that typically means that more ABSs are required. But here we observe not only that the proposed algorithm needs fewer ABSs, but its sensitivity to the height of the buildings is smaller, right? So this has a smaller slope than the curves corresponding to the other algorithms. And finally, we plot the mean number of ABSs versus the minimum rate that we would like the users to receive. So here we observe a similar effect, right? Of course, for the greater this minimum rate, the more ABSs we require. But we see that with the proposed algorithm, the number of ABSs is significantly smaller than for existing algorithms. Remember that these algorithms used other channel models that are less accurate, and also their placement criteria are less sophisticated than in our algorithm. So to sum up, we have so far discussed how to solve the ABS placement problem using tomographic radio maps. The goal was to optimize the ABS locations to minimize the number of ABSs, and at the same time warranting that every ground terminal receives at least a target minimum rate. We proposed an algorithm which is based on a discretization of their space together with a convex relaxation, okay, and then we derived an ADMM method with our solver with low complexity. It's linear in the number of grid points. It can accommodate flight constraints as opposed to most schemes in the literature. And although we focused here on an unlimited backhaul, the general cases and as well as other extensions are discussed in our journal paper. There is also an simulator that we wrote and that we published here. This allows anyone who wants to develop aerial base station placement algorithms to compare them with those in the literature, and also to compare them within this controlled environment, is using the tomographic model essentially. So now let us go to the second problem, where tomographic radio maps are applied for path planning for aerial relays. So suppose that a certain mobile user is out of the coverage region of a terrestrial base station. So our goal will be to deploy two aerial relays to establish a connection link between the base station and the user through these UAVs, right? So this, therefore, this communication takes place in 3 hubs. So the UAVs need to adopt positions in the airspace so that these links can be established and have the necessary rate, right? So here we can see the user is here, the base station is here, the UAVs took off in the base station, although they can take off at arbitrary locations, and UAV 1 followed this trajectory, UAV 2 followed this other trajectory. So the communication link will go from here to here, from here to here, and from here to here. So UAV 2 had to come here because this user is behind these buildings, right? So it needs to have go to a point with a good channel to the user, and this one should be at a sufficiently a good point that allows achieving a sufficient rate between this UAV and this UAV, as well as between this UAV and the base station. So in this context, there has been quite a lot of work Some papers focus on a single UAV. However, just one relay is not sufficient to solve the problem when there's a big obstacle between the base station and the user, right? So generally we need 2 or more UAVs. And these works have considered multiple UAVs, but they suffer from a high complexity and they cannot accommodate obstacles, buildings, or no-fly zones, right? So they need that the volume where they work is like empty, and that doesn't really work, or it's not really useful in practice. So the contribution of this work is a path planning algorithm for 2 aerial relays. Okay, the trajectories are approximately optimal, and they are obtained with a low complexity, and the scheme has enough flexibility to accommodate any shape for the allowed region where the UAVs can operate. The scheme also allows for moving user, but that case will not be considered in this talk for simplicity. It can be found in our journal paper. So let's, before formulating the problem, let's discuss, or let's have a closer look at how connectivity is established between the terrestrial infrastructure and the user. So we can distinguish 2 phases. The first one is the navigation phase. Here the UAVs take off and fly to the positions that they need to adopt in order to communicate or to serve the user, right? So during this phase, the UAVs need to receive a minimum rate from the terrestrial infrastructure. This is for command and control. So this link needs to have at least this capacity, RCC, and this link needs to have at least 2 RCC, because this is 1 RCC for this UAV and 1 RCC for this other UAV. And after they reach their destinations, they establish communication with the user. So they need to provide the user with this target rate. Therefore, this link needs to have at least RUE min, and the other 2 hubs need to have the same capacity as before, plus this RUE min. Observe this terminology. We call this one UAV 1 and this one UAV 2. We will be focusing here on minimizing the connection time as our metric. Okay, the connection time is essentially the duration of this navigation phase. We will be also assuming that the user is static, but the case of other objectives are optimized in our journal paper. So please see this reference for further information. So to formalize the problem, let's define or denote the location of UAV K at time t by this symbol here, QK of t, and then let us introduce the matrix Q, which which contains both the position of UAV1 and the position of UAV2, and we are going to call this matrix a configuration point because this is the terminology used in robotics. And therefore a trajectory is nothing but the sequence of configuration, or the set of configuration points, right, that is UAVs adopt, right? So we consider that the time starts at 0. And therefore the connection time can be expressed in this way. Here RUE of Q is a function that returns the rate that the user receives if the UAVs are located according to this configuration point, right? So the connection time is therefore the smallest t, such that the rate that the user can receive is at least the target user rate, okay? So the problem is given the position of the base station, given the position of the user, and given the maximum speed of the UAVs, as well as the target user rate and the command and control rate. The problem is to minimize the connection time with respect to the trajectory of both UAVs, subject to the constraint that the configuration points must be in what we call configuration space. So this is the set of all allowed configuration points. That means that this is the operation region, the 3D airspace, excluding the buildings and no-fly zones. Then we have the constraint that the initial location should be at the base station for both UAVs, although this is just for simplicity, they can take off from any place. And the rate that the UAVs receive should always be at least RCC, right? This constraint should never be violated. The user may receive a rate smaller than the target user rate, but all UAVs should at all times receive at least the command and control rate. And the speed should be less than or equal to this maximum UAV speed. So as in the previous problem, the rates which show up here and here, they depend on the channel, right? So to predict that, we will be using a radio map, as before, actually. Tomographic radio map again. The challenge is, as we'll see, the high complexity. So first of all, the optimization variable is a continuous function over time, right? So that means that finding an exact solution to this problem will not generally be possible. Instead, the most we can hope for is to find a valid trajectory with a reasonably short connection time. So by valid, we mean that the user is served eventually, right? So feasible means that it satisfies the constraint, valid means that it satisfies the constraints, and the objective is finite. There's a finite connection time. Okay, so we, instead of aiming for the optimal solution, we will just have to be happy with a suboptimal, a reasonable suboptimal path. To do that, the first step is spatial discretization. Okay, so we discretize the allowed flight region by defining a grid and removing the points inside buildings, inside no-fly zones, and so on. And then we also discretize the trajectories over time. So this means that with this notation, this means the configuration point at the nth time instant, or sampling time instant, right? Then what we now have is no longer trajectory, like the position for every time t, but only a sequence of configuration points, right? So this is what we call a path, right? So trajectory means like a continuous time, and path means discrete time. Okay. So now the problem is discretized both in space and in time. Each of these configuration points must take one out of a finite set of possible values. So if one sees this such a problem over a discrete space, the natural approach to consider is shortest path algorithm. However, this suffers from the curse of dimensionality. Note that these points are in 3 dimensions, and that we have pairs of points. So the number of combinations, so from every configuration point we can go to a very large number of configuration points, right? There are many adjacent points, and that means that the complexity of shortest path algorithms for this case is prohibitive, right? If it was just one UAV, it would be easy, but with 2 UAVs, the complexity is much higher, right? It scales exponentially in the number of dimensions. So let us see to how we can solve this problem, and to that end, let's adopt a slightly more abstract perspective. Let's see. Remember that we are after this sequence of configuration points, which are in six dimensions. Suppose for a minute that instead of a 6, this is a 2, right? In 2 dimensions, right? We could represent the configuration space, right? So the set of possible queues, not taking into account the discretization, right? So this the set here, right? This, the airspace excluding buildings and no-fly zones. So we could represent it by like a rectangle here. In 6D we cannot make the figure. So this is the configuration space, and these areas here, these dark areas, denote configuration points where that are not allowed because the UAVs would not receive the rate necessary for command and control. So the starting point, both UAVs are at the takeoff location, and at the end they are in positions. Each one is at positions that can serve the user, and there is an optimal path, which here is indicated by or optimal trajectory, which here is indicated by this red curve. So this is, as we said, impossible to find using things like shortest path. So to solve this kind of problems, in the robotics literature, they have considered this algorithm has been proposed. It's called probabilistic road maps, and the idea is very simple. So the idea is to generate a finite set of configuration points at random. These are denoted by these orange circles. So essentially we generate configuration points, and we remove those that fall inside the dark regions. After that, we connect each configuration point with its nearest neighbors. If the UAVs can go from each one configuration point to the other configuration point on a straight line, right, without abandoning this the allowed region, right? So this one cannot be connected to this one, for instance, because it would need to go through this part here. So after this graph is created, we can apply a shortest path algorithm. So here, since the number of neighbors of each configuration point in the graph is small, applying this kind of algorithms is possible and very efficient. Okay, so as we the shortest path is denoted here in green. Okay, so as you can see, it differs meaningfully from the optimal path. So the problem with this approach is that if we would like to get something better than this, right, we would need to increase a lot the number of configuration points, right? So think that the denser is the set of configuration points in this configuration space, the more closely this shortest path will resemble the optimal path. However, we are in 6D, right? So if we want a dense set of points in 6 dimensions, that takes a very, very large number of points, and that makes would make the algorithm very costly, right? So in this paper, what we do is to propose a smart way of sampling. So the idea is not to generate configuration points for uniformly across the configuration space, but to generate the configuration points randomly, but near the optimal path. So to do that, the idea is to first use a heuristic algorithm to plan a path, an initial or a tentative path from the starting point to the end point. This one will not be optimal, but will be near the optimal path, and then we sample near the this tentative path. Okay. So with the same number of configuration points generated at random, we get a much higher density of points around the optimal path than plain vanilla probabilistic roadmaps. So here with these points we can similarly create a graph and find the shortest path, right? So if we compare this with probabilistic roadmaps, we see that the proposed algorithm results in a path that is much closer to the optimal path. So let us apply this idea to the problem at hand. As we said, the first step was discretization of the flight region. Then we plan the tentative paths using this heuristic algorithm that I will describe soon, and then we use the same approach as in probabilistic roadmaps. We sample around that and we plan the path using the resulting graph. And finally, we, of course, from the sequence of configuration points, we need to apply an interpolation algorithm to recover the trajectory. So how to plan how does this heuristic algorithm work? So the idea is to, in our algorithm, we first find the path for UAV2 using assuming that UAV1 is at all times in a suitable location that can provide UAV2 with sufficient rate. Since due to this assumption, we only need to consider the locations of UAV2, and that allows us to apply shortest path algorithms. Okay, and then after we get the path for UAV2, the path for UAV1 can be computed using another algorithm. If that is not possible, what we do is to lift the path of UAV2, right? So we increase it, we raise it one level, and we repeat, right? We try again to find the suitable path for UAV1, and it can be shown that at some point it becomes valid. It is possible to obtain such a path for UAV1, and that results in a valid path. So I don't have time for more details regarding the heuristic algorithm. Now just let us show some experiments. Here we compare the proposed algorithm with 3 benchmarks, also in an urban scenario. So here we have on the bottom the proposed algorithm, and the others are the benchmarks. We see that the proposed algorithm goes quickly to positions, or sends the UAVs quickly to positions that can serve the user as fast as possible. Actually, I didn't mention, but the algorithm is actually optimal in results in an optimal trajectory, optimal path, sorry, in certain circumstances. I can show it again, so you can see that it goes to the good place and the rate goes up quickly. So these are some simulation results. If we compare with the benchmarks, all the metrics are better. So mean UE rate, it goes fast, quickly. Time to connect, probability of failure, and so on. So to sum up, we have considered the problem of planning the trajectory of 2 aerial relays. Spatial, we discretized the problem spatially and over time. Then we used a heuristic algorithm to plan the iterative, tentative path, sampled around it, and then applied shortest path algorithm on the graph, the resulting graph. It has theoretical performance guarantees, as I mentioned, and it works well as per our simulations. So, to sum up, we have discussed a large number of applications of communication UAVs. In particular, we have solved 2 problems that arise in this context using radio maps. For more information, please see our journal papers as well as our conference papers, which you can find at our website. Please visit it if you want to know more about us. And that's it. Thank you very much for your attention.